It flew where no spacecraft had gone before. And when Parker Solar Probe plunged into the solar corona in fall 2021, it approached our host star to within 13 million kilometers. But now, NASA's Icarus has struck again and significantly undercut its previous approach record. But how is this even possible? How can a probe get up close and personal with the sun without instantly burning up? And above all, what scientific insights has Parker Solar Probe gathered in the extreme world of the solar atmosphere? A brief anecdote from the author's childhood. When I was little, one of my friends suggested that you could simply send a spacecraft on a mission to the sun by covering it in lots of sunscreen. But since NASA obviously didn't have enough sunscreen in stock, they decided instead to send a special spacecraft to our mother star with Parker Solar Probe to take knowledge about our source of warmth and life to a whole new level. But how is it that the renowned space agency is actually following in the footsteps of Icarus? And what technical tricks are behind the fact that this time the reach for the sun did not end in utter disaster? The impossible world of the solar corona. It's an undisputed fact that the solar corona, the sun's outer atmosphere, with a temperature of 1 million degrees, is deadly. Radiation, rapidly accelerated particle streams, and searing heat make it a place of cosmic extremes. And yet, this area of all places also holds the answers to some of the most important questions in solar physics. After all, the corona is the source of the solar wind and acts as a driving force for some of the most formative processes in our home system. One of the biggest mysteries of the corona is its impossible heat. This zone is actually over 200 times hotter than the surface of the sun. But that's not all. In the lower corona, the temperature increases by almost 1 million degrees within just a few hundred kilometers of altitude. Just as if it were getting warmer in a room the further you move away from the heater. This is problematic, to say the least. According to the second law of thermodynamics, there is simply no heat flow from the cooler to the warmer. In other words, the corona cannot be heated by the solar surface, only by an internal process. However, the nature of this process is still hotly debated. One theory is based on the magnetic field lines of the sun, which, similar to a strung-out guitar string, oscillate back and forth and conduct energy from the surface into the corona. On the other hand, there's the approach that the immense corona heat is due to the explosive contacts between the magnetic field lines. In these so-called reconnections, the electric fields between the field lines suddenly collapse, releasing energy in the form of heat and waves. Ultimately, however, the key to the heat puzzle could lie in a combination of the two, or possibly even further, unknown mechanisms. And experts realized they could only reveal the secrets of the solar corona if they sent a spacecraft straight into it. Why Parker Solar Probe didn't melt. But how on earth is that even possible? How does a spacecraft manage to withstand not only temperatures of 1 million degrees Celsius, but also a relentless bombardment of radiation? At first glance, it seems almost like a miracle that Parker Solar Probe hasn't melted long ago, because there is simply no material that could withstand such extreme temperatures. But on closer inspection, we realize that it's indeed possible to outsmart the scorching heat. After all, there is a difference between temperature and heat. From a physics point of view, temperature is a measure of the kinetic energy of a particle, which is why the air temperature only indicates how fast the air particles are moving. Heat, on the other hand, describes the amount of energy transferred by those particles, and it increases with the density of particles. And, if you like, this is exactly the loophole that NASA's experts took advantage of. Because although each plasma particle in the solar corona has an extremely high temperature, there are comparatively few of them. Due to this relative spatial emptiness, the surface of Parker Solar Probe's heat shield heats up to only about 1,400 degrees Celsius. And yet, this would still be hot enough to turn all unprotected parts, especially the sensitive measuring instruments, into a pile of ashes. To prevent this, the approximately 3-meter-high and almost 2.5-meter-wide probe was equipped with a 2.5-meter-wide, 12-centimeter-thick heat shield made of carbon foam, embedded in 2 carbon plates. Furthermore, the outermost layer of the shield was given a white ceramic coating, a material that reflects solar heat particularly well. As a result, the thermometer behind the heat shield only climbs to 30 degrees Celsius. To ensure that this fundamental protection is always precisely aligned with the sun, light sensors along the edge of the shield trigger an alarm as soon as they register direct light. The onboard computer then corrects the position of the probe, and components that cannot be permanently shielded are protected by a special alloy of titanium, zirconium, and more, with a melting point around 2,350 degrees Celsius. The tungsten chips and the electrical wiring made from the heat-resistant rare earth metal niobium also help to ensure that Parker's solar probe remains in excellent condition and continues to provide us with unprecedented insights into the extreme world of the sun. How Parker's solar probe made the impossible possible. After the spacecraft set out into the vastness of space on August 12, 2018, the moment finally arrived on November 21, 2021. Parker's solar probe became the first man-made object to pass the boundaries of the solar corona. In detail, this solar boundary is defined by the point at which the sun's magnetic fields are no longer strong enough to hold back the streams of particles emanating from it. In numbers, this means Parker's solar probe approached our star to within 13 million kilometers. No other spacecraft has ever come so close to the sun. In view of this groundbreaking milestone, NASA experts spoke of a monumental moment for solar research. The fact that this previously uncharted hurdle had been successfully overcome was evident to experts from the measurement data on the magnetic field and solar wind, and from the camera images. Parker's solar probe entered a coronal world that otherwise only reveals itself during a total solar eclipse. And 3 times, the measurement data revealed that the spacecraft had passed the corona boundary. This confirmed that the so-called Alphane surface is not homogeneous and smooth, but instead has local protrusions and depressions. Where is the probe today? It's been a few days since that first border crossing. So what has happened since then? And where is the probe today? Well, we don't know what you did on Christmas Eve, but Parker's solar probe approached the surface of the sun at a distance of 6 million kilometers on December 24, 2024, setting a new record once again. Even more encouraging was the news that arrived at NASA a week after the solar rendezvous. The probe reported that all its instruments were working perfectly, and it was also completely intact. However, scientists will have to be patient before they can begin to evaluate the data collected during the approach. Parker's solar probe will not begin to transmit the long-awaited datasets to Earth until later in January, when its position and orientation are more favorable. In the future, 2 more close flybys of the sun are planned, of switchbacks and newly discovered structures. In fact, the first important finding occurred 2 years before the spacecraft entered the corona. While Parker's solar probe was still heading for that part of the solar atmosphere in 2019, its measurements revealed a surprising phenomenon. The solar wind has what are known as switchbacks, bends, or colloquially, hairpin curves in the particles and magnetic currents. While these hundreds of thousands of kilometers long S-shaped hooks obviously increase in number the closer you get to the sun, astronomers initially did not know the background of these short-lived switchbacks, which occurred in dense clusters. Ultimately, this mystery was solved with the help of the ESA Solar Orbiter spacecraft, which captured one of these striking kinks in the plasma directly on image in March 2022. In combination with the collected data, the experts concluded that switchbacks occur where open and closed solar magnetic field lines come in contact with each other. The most extreme of these so-called interchange reconnections appear in the characteristic S-shape and show up in the measurement data as magnetic field reversals. Furthermore, the switchback data collected by Parker's solar probe and solar orbiter also matched a previously completely unknown structure that astronomers detected in the solar corona a little later. This is a dynamic network of interwoven plasma threads, whose interaction releases magnetic energy that accelerates solar wind particles. And speaking of the solar wind, a few months ago, Parker's solar probe and solar orbiter were even able to clarify a decades-old research question and identify the pace setter of the solar wind. In fact, the probes had examined one and the same solar wind stream from different distances, and realized that initial magnetic field oscillations are converted into heat and speed further out. Now you can convert your click into a subscription. Press the thumbs up and click subscribe now to never miss a new video from us again. We'll see you soon.